is that we're going to get the syn epoxide formed like that, okay? So there are more specific forms of the peroxyacetic acid. So MCPBA is where the R group is like a methyl group. Those are the two names that I'll hold you accountable for. In the book, I think they also just write down peroxyacetic acid, okay? So I think the book uses all three of these reagents interchangeably, okay? But it's the same thing. We're going to form an epoxide in place of where the double bond was, okay? Now there is some stuff to worry about, okay? So if we start with an alkene, okay, if we start with this alkene right here, and if we use any of those reagents, okay, pretty easy, we're going to end up with our most basic epoxide, okay, like that, okay? But if we start with an alkene that has side chains, okay, there is stuff to worry about, okay? So let's look at two examples, okay? So this alkene right here, okay, and let's do another example. Let's do this alkene right here, okay? So let us look at what the epoxide is going to look like when we do this, okay? So remember, in place of the double bond, we are going to form this epoxide, okay? So let me get rid of the double bond, and I'm going to put the epoxide right there, okay? And now, look what has happened. We have now gone into sp3 hybridization at this carbon right here, okay? And at this carbon right here. Okay, this should be, sorry, coming out like that, okay? And at this carbon right here, okay? Okay. And we have made two new chiral centers, okay? We have a new chiral center there, and we have a new chiral center there, okay? So we learned in Organic Chemistry 1, if you have two new chiral, by the way, let's prove it's a new chiral center. Okay, check it out. This carbon right here, you take this group is an oxygen, you take this group, you hit this thing, you go this way, you got all this. Four different paths. And then over here is also four different paths, okay? When we have two new chiral centers, okay, remember theoretically we could have 2 to the 4, we could have 2 to the n, which is 4 different stereoisomers. We don't make 4 stereoisomers here, okay? We just make this thing plus its enantiomer, okay? We only make 2 of them, okay? So notice that these two side chains right here, okay, the things that were cis to one another, okay, this isopropyl group right here is right adjacent cis to this methyl group, okay. They end up syn to one another when we open up the double bond, okay. They're not anti from one another, okay, but we also make the enantiomer. What does the enantiomer of this thing look like? You know that the enantiomer at every chiral position is the exact opposite, okay? So just take every chiral position and switch it, okay? So that would go there, and then the hydrogen would come in the front, and the methyl group would go in the back. So this thing plus its enantiomer. What we're not making is the other 2 stereoisomers, where this thing is sticking out and the methyl group is in the back. So notice in this stereoisomer and this stereoisomer, the isopropyl group and the methyl group are together in the syn orientation, and back there, they're also together in the syn orientation. Okay? So the reason is because the substrate, the alkene, is flat like a book, okay? This carbon right here and this carbon right here, those are sp2 hybridized. These angles are 120 degrees. This molecule is flat. So when peroxidation happens, it can happen above on the front cover of the book, okay? Because the oxygen is added at the same time on both of the vanilla carbons. Or it can happen from the back cover of the book at the same exact time, okay? And as a consequence, we get 50-50, this set of enantiomers, where however the side chains were is conserved in the product, okay? So let's look at another example, okay? In this alkene, the isopropyl group here and the methyl group are trans to one another, okay? And so, again, we're going to conserve that if we use any of these reagents, whether it's peroxyacetic acid, this form of it, written this way, or if it's a specific form of whatever, it's all the same thing. Now, we're going to open up the double bond, okay? Now we got to think about what the side chains are going to look like. You see how this isopropyl group is here, okay? So that's going to be sticking out like that, okay? And now we have a hydrogen sticking out on this side, okay? And then the hydrogen is in the back over there, and the methyl group is in the back on this side, plus the enantiomer. So in this case, when the substituents are trans to one another, we end up making the anti-product plus its enantiomer. I'm going to draw the enantiomer, okay? So I could either write this thing plus its enantiomer, or I could actually draw the enantiomer. So the enantiomer is going to have at every single chiral center, it's going to have the exact opposite orientation. So the hydrogen was in the back there, it's going to come into the front there, okay? And I'm going to put that in the back. And then the hydrogen was in the front here, so I'm going to move it to the back, and I'm going to put the methyl group in the front, okay? But notice that the substituent, the isopropyl group, and the methyl group are still anti to one another, just like they were here, okay? So the point is that we conserve the positioning in the alkene in the epoxide because the geometry here is sp2 hybridized, okay? And we can get the epoxide forming above the cover of the book or below the cover of the book, okay? But it does not change the orientation of those things. So here's a very good question below, okay? What is the product of that reaction? Okay, so that's a question I could ask you. By the way, there's another set of reagents that we can use, okay? And that is, so again, all of these things mean the same exact thing, okay? But there's another set of reagents we can use again. So let us do the next problem together, okay? So what is the product of this reaction here? So this is the one on the board. This is a good test question here, okay? So again, we can use methyl and ethyl and phenyl as shortcuts. We've all agreed we can use those. Okay. So now, so MCPBA. Okay. So what is the product going to look like? So like I told you, we're going to form an epoxide. The double bond is going to be broken, okay? And this thing on the bottom is going to come out like that, okay? And then there's a methyl group that is adjacent to it, okay, cis to it. So those are going to be syn to each other. And then that methyl group is going to be in the back. And then that ethyl group is going to be in the back, plus the enantiomer, okay? So that's the right answer. Now there's another set of reagents that will also do this. And in that case, you need to know the mechanism. Okay. So let's do this one together. Okay. So not only does the if I give you this question on an exam, I'm probably just going to stick with MCPBA. Okay. So that's the one I want you to remember in terms of the peroxyacetic acid. Okay, here's another set of reagents that will get you there. I hope this looks familiar to you, at least the first part of it, okay? So this is halohydrin formation. Okay, going back to chapter 8 of Organic Chemistry 1, you should be able to do the mechanism of that problem, okay? So remember, Br2, when you have an alkene, okay, the first step of halohydrin double bond reaches out, and then we form a bridge, okay? So here's the bridge that we form, like this. So the BR is like this, okay? And then we have the ET, and then okay. And then we have attack of the H2O, and the H2O is going to attack the less substituted carbon. So I would not give you this version of the problem, okay? Because this has complexity in it. We get a mixture of products. But I could ask you, what is the product of this reaction? And this also will end up conserving this will also end up conserving the stereochemistry. Okay, so you'll end up with whatever the side chains are on the same side. But let's do an easier one so we can see what's going on. Okay, so this one is a little tricky because we could get a mixture of products. This is not a good example. So let's do a good example. Let's do one like this. Okay, so here's one. Maybe I won't ask you for the mechanism of this thing. Okay, so very simple, but I want to show you what's going on. And then step 2, NaOH. Okay, so you know that we're going to make the bromine bridge, okay? And then what's going to happen is halohydrin formation, okay, is the H2O is going to attack, okay? So the H2O is going to attack, and this is going to leave. And remember that because of the bridge, the H2O is going to attack on the opposite side, okay? So remember that when this reaction takes place, we end up making the anti-products, okay? And then we deprotonate, and we end up making the anti-products of the halohydrin reaction, okay? So in the next step that happens, so this is something we did not learn in chapter 8, then we put in some sodium hydroxide, okay? And that can partially deprotonate this OH group, okay? And then we get the deprotonated form. Let me make sure I get this right. Okay. And then it attacks. So when it attacks this carbon right here, this is in the front, so it's going to attack from the back, okay? And that's why we end up making the this form of the alkoxide, okay, which is the same thing as the syn form of the alkoxide that's drawn like this, okay? So that's another way of making the alkoxide, okay? And it's also a way of conserving whatever the side chains were. Okay? Maybe I won't ask you the mechanism of that question. Okay? Only because we don't want to get a mixture of products. Because when you're forming the halohydrin, there's complexity there. Okay. But I could ask you to predict the products. Okay, predict the products. Okay, so now we're going to move to the end of the chapter real quick, because I don't know why they put this at the end of the chapter, because this is related to the stuff we're just talking about, okay? But this is at the end of the chapter. We're going to talk about asymmetric epoxidation, where we can just end up, when we do this reaction right here, we end up making a set of enantiomers, okay? Remember, organic chemists do not want to make more than one molecule, okay? So when we have these two enantiomers right here, we don't want to sell something that's 50% pure, okay? We want something that's 100% pure. So the person who invented this technique invented a way of making a 100% pure, okay, just one of the epoxides is going to be formed. And that's why the guy won the Nobel Prize for this reaction, okay? Because epoxides are very useful. And getting pure epoxide is incredibly useful. Okay? So we're going to learn this. It's called Sharpless after the person who invented it. Asymmetric epoxidation. It's a very cool thing that they did. But for some reason they put it at the end of the chapter, and it should be explained right now. So if you're wondering what happened, this is what happened, okay? So in this case, I would ask you to predict the products of this reaction. So this is a little bit complicated, okay? It's probably one of the harder things you're going to do in this chapter, okay? So we're going to start with some sort of alkene, okay? So we start with some sort of alkene. Now, if we start with this alkene, and I presented these reagents to you, MCPBA, okay, or the halohydrin and then NaOH, okay? And if I asked you to predict the products of that thing, you could do it, okay? So don't panic, there's just a hydrogen right there, and there's a hydrogen right there, okay? So we're gonna open up that thing, it's gonna be like this. This thing is gonna come out in the front, okay? So 1, 2, 3. Okay. That's going to be in the back, the OH group. Okay, sorry, that's the carbon right there, OH. Okay, and then we write plus the enantiomer. Okay, so we would have made that thing plus its enantiomer. Okay, so you know how to do that now. So all of these reagents. Okay. Now we're going to learn how to make just this thing, or just its enantiomer alone. Now, in order to do this, though, there are some restrictions, okay? One of the restrictions is that in order for this to work, our alkene must have an allylic OH group, okay? That's one of the rules, sorry, okay? So what that means is, remember that when you have a double bond, okay, the carbons that are participating in the double bond, those are called the vinylic carbons. And the carbon adjacent right here, okay, that is the allylic position. Okay? So the allylic position is the position adjacent to the double bond. Okay? And the rule is to get this asymmetric reaction to work, where we only make one enantiomer, okay, we need to have an OH group at the allylic position. Okay. What we're going to use is we're going to use an asymmetric catalyst. So we're going to use a molecule that's going to hold on to the allylic hydroxide group and sort of block like the front cover of the book or the back cover of the book, so that the reaction can only take place on one cover or the other cover. Okay. If we use the let's see how we're going to do this. So the first thing you're going to do is you're going to take your alkene and you're going to put your alkene, okay, in a box, and you're going to draw it such that the allylic position is in the right-hand corner of the box. Okay. Let me actually redraw this really quick. Sorry, I did not like how I drew that. Okay. There we go, okay? So there's the double bond, and there's the OH group. So if our starting molecule looked like this, okay, that could be the starting molecule there, okay? Let's do another one, okay? I'm going to draw this one in a different orientation to show you. This still has an allylic OH group, okay? This molecule here. Let's say we want to do sharpless asymmetric epoxidation of this molecule. Okay. The number one rule, the first thing we have to do is we have to draw that molecule in a box. By the way, we're not done with this molecule. Okay. So on this side, we have 1, 2, 3, 1, 2, 3. Now we've drawn this molecule in this box. So notice that this vinylic carbon right here has a hydrogen here, and that one has a hydrogen there. So once we've drawn the OH group in this corner, there's a hydrogen right next to it on the same vinylic carbon. So that's over there, okay? And then the other substituent on the other vinylic carbon is anti to it. So I'm drawing an anti to it. And then that carbon, vinylic carbon, has a hydrogen, so it's right there, okay? So the first thing you have to do is translate your that the OH group is in the upper right-hand corner. Now let's do it for this other thing too, okay? Drawing this first, so this is always going to be the same. Okay, now, notice on this vanilla carbon right here, okay, there's a methyl group on the same carbon that the OH group is on. So I know that there's a methyl group right there, okay? And then when I go down to this side, on the same side of the OH group on the other carbon, okay, is an ethyl group. So that's going to be like that, okay? And then there's a hydrogen right there, so I'm just going to draw the hydrogen right there, okay? So you got to translate your alkene when you're doing this problem into the box, put the OH group in the upper right-hand corner. Okay, there's two different kinds of asymmetric catalysts we can use. We can use the plus DET version. So that's a good thing about multiple choice, okay? You don't have to remember it's TIOCA, blah, 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 okay? I'm not going to trick you and make the wrong answer have like 3 right there, okay? But what you have to remember is there's a plus DET version and a minus DET version. And that's what I'm talking about, the asymmetric catalyst. It's a molecule that's going to hold on to your alkene, okay, with the back cover block or the front cover block, okay? And that way only one side is going to react with the, and this is the peroxidase that we're going to use in this case, okay? So you got to remember what happens with plus DET and minus DET. Okay, let us start with the plus DET version, okay? So that's the easiest one, okay? So if it's plus DET, after you draw your molecule in the box, okay, you are going to draw the epoxidation happening like this, okay? And then you're going to turn your paper and voila, that is the right answer, okay? So redraw that, okay? But of course you're going to lose the double bond, okay? And so the OH group is going to be sticking out like that, okay? Like that. And so what is back there? That's a hydrogen, okay? Because there's nothing drawn there, okay? And then in the front is a hydrogen right here. Don't get confused, okay? That's the hydrogen, okay? And then in the back we have this, this propyl group back there, okay? That's the only molecule we're going to make, okay? So if you follow these rules, you can't really mess this up. You probably can't. Okay? You only make one molecule. So as a wrong answer, I always write plus the enantiomer, and half the class choose that answer, okay? Remember, this is the sharp, and I'm going to write on the test, what is the product, sorry, I got to put the S there, okay, of this sharpless enantiomeric epoxidation reaction. And then you're going to look down and it's going to have your alkene and it's going to have this set of reagents with plus DET or minus DET. And you can rule out any answer that has something plus its enantiomer. Okay, we're only going to make one. However, now you've got to worry about if you chose the right enantiomer, okay? Because I could have had the wrong enantiomer, okay? So, let us review. If it says, that's the question at hand, you're going to take your alkene, you're going to draw it in a box, you're going to put the OH group in the upper right-hand corner, and then you're going to translate the rest of this into this. That's hard to do, so you've got to practice. If it says plus DET, you're going to draw the O group like that, you're going to turn your paper, and that's the right answer. So you see the OH is coming out. If it says minus DET, okay, that's the other catalyst. My advice to you is to draw everything the same, draw this thing like it's plus DET, but then in the last step, you're going to draw the enantiomer of this thing, okay? So this thing is going to come in the front, okay? And that is the only product you make if it's minus DET, okay? So my advice is do everything exactly the same, whether it's plus or minus, okay? Except if it's minus, in the last step, translate it into its enantiomer, okay? Red flag. The wrong answers will have plus the enantiomer there. Okay. You will get enantiomers if these reagents are being used. Okay. But if you're doing the asymmetric epoxidation, you only get one molecule. Okay. So that's probably one of the hardest problems you're going to have. Okay. So let's do this one together. Let's say it says minus DET. Okay. So I'm going to put the O there. Okay. I'm going to turn it around. Okay. Zoom in. Okay. I'm going to draw the, so it says minus. So the last minute I'll change it. So the hydroxide is coming out in the front. The methyl group is in the back. The hydrogen is in the back. The ethyl group is out in the front. Okay. Now, since it says minus and not plus, at every position, I just gotta switch it. Okay. So this is going to be a hydrogen, and that is, oops, that's sorry. And that is that. So that would be the minus DET for that. This would be the plus DET. Okay? Now, you got to follow my rules exactly. If you're drawing your oxygen on this side, everything falls apart. Okay? If you're not putting the OH group in the upper right-hand corner, it's not going to work, etc. Okay, we're moving on now. Okay? So you got to know the mechanisms of every single one of these reactions, okay? But it's not hard, and the same thing happens over and over and over again, okay? So epoxides have two general kinds of reactions that they undergo. They either undergo nucleophilic ring opening, or they undergo acid catalyzed ring opening. These are all the nucleophilic ring opening reactions, okay? And so they all pretty much go the same way, okay? So whatever reaction we have, let's do all of them really fast, okay? So you need to be able to do all of these mechanisms over here. So of the 5 or 6 questions from this chapter, high priority is naming epoxides, Williamson ether synthesis, the ether reaction, the sharpless asymmetric epoxidation, one of those, and then something we still have to talk about, which is acid catalyzed ring opening, we're going to talk about tomorrow. Okay, so let's start with the first set of reagents. NaOH, okay, and then 2 is H2O. So first of all, the first thing you're going to do is notice that we have an epoxide, okay? So this means you're doing probably nucleophilic ring opening or acid catalyzed ring opening. Well, if you're doing acid catalyzed ring opening, you would see acid above the arrow, okay? That's what acid catalyzed ring opening looks like. If you don't see acid, then you're doing nucleophilic ring opening. So you notice all of those reagents right there, sodium hydroxide, sodium methoxide, sodium cyanide, sodium thiol, Grignard reagent, lithium, aluminum, none of those have acid in them, okay? So that means you're doing nucleophilic ring opening, okay? So the first thing you're going to do is you're going to take the first reagent, most of them have a carrier cation, sodium, remove the carrier cation, so what's left? Hydroxide, okay, or whatever's attached to it, okay? And you're going to do an SN2 reaction where you attach the less substituted alpha carbon to the oxygen, okay? And then the bond that's connected from that oxygen and that carbon to the oxygen is going to leave, and it's going to go onto the oxygen, okay? So here is your first intermediate of this reaction. Nothing happened on this side, so make sure you don't mess with the stereochemistry of this side. And then this thing left like that. Well, count the number of carbons that you have, okay? So you have 1, 2 carbons there, okay? 1, 2 carbons there. This carbon has the oxygen attached to it. When it leaves, it takes on a negative charge, okay? And that's okay because we're in base right now, okay? So we're already in a solution that has negative charge. So it's not freaking out, just that's the new normal, okay? And then you can guess what happens next. okay? In step 2, we're going to protonate that thing. Sometimes it's H2O, sometimes it's hydronium, okay? So, and then bam. And so this is the product of this reaction. So we make a diol, okay? So a diol like that. So that is the product of this reaction, okay? And all of these reactions from that first one into the second one, pretty much go the same way, okay? So let's do the next one now, okay? Remember to attack the less substituted carbon. So there's 2 carbons here. One of them has a substituent on it, one of them does not. Because this is an SN2 nucleophilic substitution reaction, okay? So the next set of reagents is sodium methoxide, okay, or it could be like sodium ethoxide or whatever, okay, and then H2O or H3O plus whatever. So the business end of this is the methoxide in this case. So here's a way of making an ether, okay. So we're going to attack the less substituted carbon at the same time. That's going to open up, okay. So again, keep track of. Now I'm not going to draw that. I'm going to draw it like this now. So don't get just. There's that, there's this thing is still sticking out, and then we have this thing, okay? And then in step 2, we're going to protonate that thing, we're going to protonate it, okay? Let's do the next set of reactions. Sodium cyanide, okay? So only 2 kinds of reactions with epoxides. We're going to either be doing nucleophilic ring opening, which is all of these, or we're going to be doing acid catalyzed ring opening, which we're going to talk about tomorrow. That has an acid. That has a different mechanism, okay? So we'll talk about that tomorrow, okay? But all of these have the same sort of thing basically happening. Okay, so cyanide is going to be the nucleophile. And so here we have our substrate again, okay? So what are the intermediates? So let's look at this intermediate, okay? So be careful. So there's the carbon. So this is cyanide. So this has become a nitride. So this is called a nitride. And then when we protonate it, I'm going to move ahead, okay? So this is the product of this reaction, but I want you to know the mechanism, which means I could ask you for the intermediates. So I've skipped ahead. You know that there's a deprotonated intermediate, okay, before step 2. So these nitriles are very important. We're going to study them in chapter 20, I think, or 21 or something, okay? Because when we add a cyanide group to a molecule, from here we can make carboxylic acids, we can make amides, we can make a lot of different molecules with cyanide. That's why cyanide is so common in chemistry labs, even though it's incredibly dangerous, okay? It's very useful for synthesis. Okay, so that's what. The next one, okay, thiol. Okay, you can guess what, if there's a sodium in the front, okay, then whatever it's attached to has a negative charge. Sodium is a carrier, so that's going to be the nucleophile. Okay, I'll leave that one up to you. Let's try our Grignard reagent. Okay, so don't panic. So you know that is a Grignard reagent right there. So what is the nucleophile going to look like? It's going to look like this. Okay, so here we're going to be using this to attack our, again, the same exact position, the less substituted alpha carbon. And in this case, we're going to be adding a methyl group to make a longer chain carbon, and then we protonate, and we're going to make that thing right there. Okay, so we could do this with Grignard reagents or carbon nucleophiles. We just learned about those in chapter 12. And then up there, what's going on in the last one? Lithium aluminum hydride. We can transfer a hydride over. Okay, so remember, aluminum hydride can donate a hydride because so we have this right here, another nucleophile, a hydride nucleophile. Okay, same thing. We're going to take the entire hydride, go over there. We learned this in chapter 12. Okay. Now be careful with this. It's just a hydrogen. Okay, so that can get a little confusing. We have this intermediate here. Okay, and then we protonate that thing, and we end up making this alcohol right there. Okay, so it's not that bad. Okay. So in all of those cases, I could ask you, what are the intermediates and or products along the reaction coordinate. But before you go, let me just show you one piece of complexity that can come up in these problems, okay? So one piece of complexity that can come up, let's look at this example right here, and then you can go, okay? So here we have some stereo issues, okay? So it says here cyanide, okay? Cyanide, okay? So that's still nucleophilic attack. So what were the rules again? Okay, the rule was that we're going to take off the sodium, okay? Now, which of these carbons is going to be attacked? The less substituted carbon, okay? So this carbon right here, okay, has 2 carbons attached to it. This is a hydrogen, okay? This carbon right here has 1, 2, 3. This is a tertiary carbon. This is a secondary carbon. So we're going to attack the secondary carbon, okay, because it's an SN2 reaction. Assuming we have all the time in the world, eventually this position is going to be attacked, more so than this one, okay? Now let's draw what happens here. Now this is where we have to be careful. On this side, nothing changes, okay? So don't mess anything up in terms of the stereochemistry on this side. And we do release the oxygen, okay? That's still on the plane of the paper. But on this side, there is an inversion of configuration, okay? Because this is a chiral center right here. Okay, this carbon right here has an oxygen over here, an ethyl group going this way, a different path. So we need to change it, whatever it is, from an R to an S or an S to an R, okay? Remember, SN2 reactions have an inversion of configuration. There's an easy way to do that, okay? You take whatever is sticking out in the front, okay? You keep it sticking out in the front, but you move it above whatever is in the back. And then you attach the thing that you're attaching in the plane, okay? So I'm putting this in the plane, okay? And then I'm taking whatever's sticking out and just moving it above. That inverts the configuration automatically. We'll talk about that a little bit more tomorrow. And then we protonate in a second step, so that's the product of this reaction. Okay, that's enough of it.